Thursday, 48 multiple choice questions. That will not take you the entire period. I can let you know exactly how you did. Okay? Now the one thing that you might not like that I'm going to do is just to make sure that you are reminded by it. I'm going to put those final exam multiple choice scores into the final exam category, which means it's going to look, even if you have a perfect score, it's going to look like you got a 40% in the final. I am not activating the grade. I am not setting the grade. I'm just putting it in so you know where you're at. Okay? I'm not activating it. Only you, and honestly, only you will be able to see that. So again, don't freak out when I do that, because the grade's going to adjust, and you need to know that adjustment. So, what topic first? I can't do everything. There's no way. Also, who's joining me after school today?
Today.
Awesome. Also, when are you going to take your quiz? Remember, when are you going to take your quiz?
I don't know.
Okay, I put a 0 in just to let you know.
Okay.
Okay.
Wait, sorry.
Number 7? Can you explain what happens to intermolecular forces, phase changes, IAM, da 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 da? Okay. So, make sure. Okay.
Wait, is this the 5-step problem?
Nope.
Yeah, okay.
Well, it's not the 5-step problem, it's the explaining the 5-step. But no, there's no math, because what you asked for is just, can you explain this diagram? So no math. This is no math. And also, before I forget, there will be no limiting reactant problems on the final exam.
What is that?
The limiting reactant problems is when you take 2 stoic problems, compare the answers, and then tell me what answer it is. It was not on your final exam review. I totally forgot to put it on there. Therefore, I told you that's what it was on, so limiting reactant is off. Now what I could do is I could still give you 2 5-step problems, just make you do them separately.
Wait, so look, yeah, do that instead of.
That's actually hard.
What?
I plan on staying until 7. I'm essentially going to stay here until it's very clear that everyone's good. So yeah, I'll stay until 7 if you. Yeah, today, tomorrow, and Wednesday. Yeah. Today, tomorrow, and Thursday. I'll stay afterwards too. And I'm also staying extra, actually Friday I might not be able to. Oh, sure. So, what's happening here? Number 1. So, Taylor, where are the phase changes occurring? 2 and 4. Okay. The phase changes are happening on stages 2 and 4. Okay, that's actually a really big concept for this. It actually explains why, when you're doing Q, that you have to use this equation. Okay, there is no delta T, so you can't do Q equals MC delta T. The change of temperature for 2 and 4 is 0. So your whole energy would be 0. But obviously that's not true, right? You grab a thing of ice, it melts in your hand. Obviously there's an energy change going on. And again, that's why you need to know how much energy it takes to break up those bonds and do it again. Again, fusion, vaporization. Vaporization, boiling, fusion, melting, freezing, stuff like that. So one of the questions that it's asking is, for example, the intermolecular forces, right? And we talked a little bit about this last week a little bit and 2 weeks ago. But with IMFs, so Taylor, I'm going to go to you on this one, because Jolly took your other one. What number, 1, 2, 3, 4, 5, are the intermolecular forces the strongest? I will tell you it's only one number. And I will say that you're 50-50. It is 1 or 5. You were correct. Which one do you think?
5.
Okay. Okay, so if you had to bet money, the next number you say, if you had to bet money, would it be 1 or 5?
1.
It is 1. Okay? Take her to the racetrack. It is 1. And Taylor, why did you go between 1 and 5? I like how you did. I know you went to low temperature and high temperature.
Because I knew one of them was like,
Good. What is water here?
oh, that's either it's all melted or ice.
It's all ice, right?
Ice.
It's all ice. So it's a solid, right? And it's all solid. And solids have a very strong intermolecular force because they're very close together. So the weakest is 5 because it's all gas, and gas particles are really far apart. And that's really a big deal with this. Again, solids, very, very strong intermolecular force. Everything's right on top of each other. And then they get up further and further away. Again, intermolecular forces are the forces between. And that's why I put that last question on the quiz on there. Now, I don't say anything because someone in here hasn't taken the quiz. But there's a reason why only one of you in this class got that question right. Okay? You've got to know the definition. Okay? You've got to know the definition. And again, that's really the IMF part. Now, the other thing that it's asking is, during the phase changes, what's happening to IMFs? So, let's just say that you're going up. Okay, you're going from 1 to 2 to 3 to 4 to 5. Are the intermolecular forces getting stronger or weaker going up?
Weaker.
Weaker. And it's because the particle's getting further and further apart. And if I'm going down, like I'm starting to freeze it or condense it, the IMFs are going to get stronger because they're getting closer and closer together. Excellent. And then the only other last thing to really talk about with this diagram is kinetic energy, which I'm going to do in green. Kinetic energy is related to temperature. That's KMT number 4. So the higher the temperature, the more kinetic energy. During a phase change, what's happening to the kinetic energy? Somebody else. What's happening to kinetic energy in regions 2 and 4? This is the most probably missed thing about this. It's going up. Kinetic energy going up on 2 and 4? Why are you saying no, never mind? Because you were going up, and I see why you're saying that, but I just said 2 and 4 and you changed your mind. Why did you change your mind when I said 2 and 4? Because nothing's happened. Right.
Does it fight equilibrium?
You know what, to be honest, it does a little bit. It does a little bit. Because during this region, these are where the molecules are trying to phase change, right? And for them to be at equilibrium, for them to be consistent, here, because the temperature is at 0, and this one at 100, all those particles of ice want to become a liquid. It's too much. Zero degrees is too much for a solid to handle for water. So they're going to separate. So in a way, yes. Now again, I'm not going to bring in this in equilibrium. Okay, so you're not going to see this graph and say, talk to me about equilibrium. You will not see that. But again, when you probably eventually get up to higher biochem, stuff like that, they'll bring it in a little bit. Because the molecules want to spread out, right? Put ice at 100 degrees, that has no choice, right? It's kind of like that. Here, there's no change. A lot of times people tell me for regions 2 and 4 that the kinetic energy is going up. And again, remember when we talked about that ice melt lab and everybody was surprised? Again, you admit it, you guys were surprised when the temperature flatlined, either at 0 for some of you, sorry, or at 102-ish, sorry, for the whole class period. During the phase change, the energy is pulling those molecules apart, not speeding up the particles. So in 2 and 4, there's no change. The rest, it's either going to go up or down based on which way you're going. The energy is going up, kinetic energy is going down. But for 2 and 4, there's no change because of the phase change. The most missed thing I've seen from magnet students the last 3 years is the green. People do pretty good on the blue and black. Not gonna lie, not gonna lie. Color coding. There. Sorry, let me save this before something crazy happens. Final most missing is green. How are we feeling on this one? We okay? Isn't not too bad, right? It's bringing back the ice melt lab and the Caligula property lab. And again, we've talked about IMFs a little bit more, right? So that should be a little bit better. The kinetic energy part, which is the gas law part of this. This diagram is really awesome. Okay, like I'm gonna be honest, you know you're gonna see something with that diagram on that test, right? Because it brings in unit 7, 8, 9. You could argue 11, and I could do 10, but I'm not going to. So this diagram brings in kinetic molecular theory, which is gas laws. It brings in solutions, because that's the diagram that you're getting at, phase changes. It brings in math, because you know how to find this with the 5-step. And it brings in intermolecular forces, which was unit 11. So this thing is on your final. I don't know which way I'm going to ask you to talk about it. Actually, I do. And we can go from there. Yep. You can go to the bathroom. And that's on video. Yep.
Is Avogadro's 96.022 times 10 to the 23?
Yes, sir. And it's on your test. Oh, absolutely, yes. No, I'm hoping to talk the entire period. My goal is this week to be so exhausted after talking with you guys that you guys don't want to talk to me anymore. Are you zooming in on this? That's gangster. So, if you would like to know, because maybe I shouldn't have put the final exam right in front of you. There it is. Yeah, the final exam is right here. So on your final exam, it gives you Avogadro's numbers on it. You are allowed to use Mole Island, okay? I will have extras in case you lost yours, forgot yours, don't like yours. Last time I checked, all of you were clean, like no one had any like problems or anything, so you guys are good. I do give you the ideal gas law. I do give you the combined gas law. I don't give you the other 3. Because technically the combined gas law is all 3, right? So I don't give you Boyle's, Charles K. Lusick. I just gave you combined. So you won't see those on there. I gave you both formulas for the Caligula properties. So the M, like the molality, the cursive M, KB, KF, I, Van Hoff factor. I gave you both of those. I gave you both R values, dilution equation, molarity, molality, Q equals MC delta T, enthalpy of solution equation, Q divided by mole. I give you the blue. I gave you that equation this time. I gave you the C value for water, ice, and steam, and I give you the delta H of fusion and vaporization for water. So that does cover everything that you would need on here. And those are honestly the big equations that we've talked about. And I give you that on the multiple choice, which I have here, and I give it to you on the free response, which is right here. Copy and paste it, looks the exact same.
Can we briefly go over 24, the kinetic molecular theory?
Yes. And then after KMT, can I do Caligula properties? Is that okay?
Yes.
That was the number 1 thing by far with everybody. Okay. You know what? If you guys don't mind. What I'm also planning on doing, just to let you know, is whatever happens, every topic I'm going to do a new slide, I'm going to print these out and give it to you for tomorrow. Okay? So you will get these. It might be smaller, like PowerPoint style, but I'll give it to you. Okay? So it might be a little bit bigger that way. So KMT. And if you, actually, can I go back to this and say, I'm going to put like what units this is into just so you kind of know. This is unit 7, unit 8, unit 9, and unit 11. This is unit 7, really. So KMT, 4 parts. And again, these are about gases. And we already talked about this one today. Kinetic energy is directly
Related to the temperature.
related to temp. I.e., at higher temperatures, particles move faster. Yeah, that makes a lot of sense, right? Once you're warmed up, you run faster, right? That's why they make sure you're warmed up before a sporting event or anything like that. Again, if it's really cold, there's not a lot of energy. So that one goes really well. And honestly, being straight up with you, that's the most important one. That is the most important one. That's the one that we've used a lot, especially in thermal. Number one. These other ones are the one that I think sometimes we forget about. This one, I think we can easily try to remember. Are gas particles big or small?
Small.
Yeah. Gas is really small, right? All atoms and stuff are really small, but these guys are really small and really far away. So we assume that gases have, because they're so small, they have no this and no this. Does anybody? Go ahead. One. No mass, correct. And no what? Because they're so small. They're so small, we say they don't have a volume. The next one was the diffusion one. There we go. Gases move through diffusion. Again, we talked about how, I sprayed this Febreze in the corner and about maybe a third, halfway through it got, after the whole period, you were able to do this. Again, with it being a little more windy, I'm sure I could probably get it everywhere if I sprayed up. We could spread it out. Again, that's that whole, walking through the hallways thing, right? How many of you have to deal with going downstairs during any of the lunch periods around that intersection down there? You guys know how busy that one gets? It's like sardines, right? It's crazy. But you have to bump your way through and you eventually be able to get through. And everybody else eventually is able to get through and spread out. That is the perfect example of KMT number 2, the diffusion part. They're going to work its way through each other. For example, if I wanted to just walk through this, I can work my way through everybody's stuff. I might have to get a little creative. I just did it in, this one's but I could easily make my way through. If I wanted to go around a Zeke like this, I could go around like that, but that's weird. I'm not about that life. That's that one. And then the last one is that. And the last one is collisions are elastic. And that means gases do this.
Yeah.
They don't slow down. It's for example, me hitting you with my car, and we just keep bouncing off and keep going the same way. Obviously, if two cars hit each other, what happens? They lose momentum. Okay, some of you that will be taking physics, you will do the math of this. You'll hit each other, they lose momentum, and they kind of crumple and stop. Gas particles don't lose the energy. They hit each other and keep going. So if cars were elastic, well, I'm not saying no one would die from a car accident, but the cars would be okay. And that's that one. Okay. And again, we assume this also because they're moving so fast and there's so many collisions, it's just like ping pong. It just goes back and forth, back and forth, back and forth, back and forth. But again, the big one is this one. This is the important one. As a matter of fact, this one's so important that I might just tell you that you need to know that one.
That's all?
I might be saying that. That's so important that if I were you, I'd focus on that. Because that's the one that transcends. That one transcends units. That one's definitely unit 7. This one also is talked about unit. Yeah, unit 8 we talk about it. Unit 9 we talk about it.
I was
That one comes back in. Are there any questions on KMT before we hit the big CP? All right, CP. CP time! Again, another unit 8. Look at the properties. Oh, click at properties. This is 24, 22, 22, 20. This was the third most asked thing. The number one most asked thing was actually 23 and then 22 by 1. Okay, so this was a special one. So, clear properties, there are 3 of them. Does anybody know what one of the 3 are? My goal is that 3 different people know the 3. Actually, here, let's start here. What's the definition of a colligative property? Let's start there. What is a colligative property? Should have kept all the crickets in the room this morning. You could have heard them. Cheep, 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 cheep. You did not want to be in here this morning. There were roaches everywhere. Yeah, there were at least 12.
You let them loose?
Yeah, let them loose out there.
No. You did?
Yeah, I took them out of the room.
You didn't kill them?
No.
They're gonna reproduce.
Why would you do that?
Well, I took them out over there outside. Jeez.
Oh, outside.
Yeah, I took 'em out.
Outside?
This
Yeah,
is
outside the room and outside the building.
This is on
Okay.
I let them out
video.
over there.
Wait,
This is
why
on
were
video.
why were they still in the bed?
It's like you know, same.
Anyway, clear property.
Report it.
Report.
Her rats died.
So, clear property. John, is that hand up? Yes. The concentration does matter, yes, but it doesn't matter what it is. So for instance, with the colligative property lab, right? During the colligative property lab, we added stuff to water and I said, hey, boil this, heat freeze this. And just from that lab, I think you know 2 of the 3. What happened, who had a really hot one? What happened with the boiling point when I added salt or calcium chloride? It went up, right? The boiling points went from 102, 103 to 118, I think it was here, 118-ish? It spiked up 16 degrees. So the first colligative property is when you add something to a solution that is pure and you make it unpure, the boiling point, can I go BP or do you want me to write it out?
Doesn't matter.
Are we okay? Okay, boiling point goes up. So for instance, maybe I should write this. BP, H2O, 100 degrees Celsius. Boiling point of salt water might be 105 degrees Celsius. Maybe an example of that. Yeah, just an example. Because again, some of you proved, I added something to cheat. So some of you spiked up 10, 12. It doesn't spike up relatively that much. Now again, the concentration does matter, Dolly, you're right. Because if I add more stuff, it has more of an effect. Some of you I added just a pinch of salt. It went up to like 105. Some of you I added like 5 pinches. It went up to 108, 109. And some people like Nate and Rory's group, I added calcium chloride, I added a bolo. That's literally a chemical quantity, a bolo. And theirs went up to 118, 120 fifth hour. Water boiled at 120 in that class. It's a crazy difference. And again, these two are related to one another. This one is that the vapor pressure goes down. Vapor pressure goes down. And this one is at the freezing point. Goes down as well. So for instance, on this one, freezing point of H2O, as you guys know, is 0 degrees Celsius. Water freezes at 0. But the freezing point of salt water is around -4, -5. So I'm just going to say -5. Those are the colligative properties. Okay, so we've done, arguably, we've done 2 labs with the freezing point going down. That was the ice cream lab. That ice cream lab is normally what we do as chemistry teachers at East. We normally do the colligative property lab for boiling point. Some people add sugar, some people add salt. You add more sugar, it goes up more. You add more salt, it goes up more. We fuse those 2 labs together so we could talk about it as a class. So some of you did boiling point, some of you did freezing. And then the ice cream lab, everybody did freezing again. Those are the 3. Are there any questions about those 3 before we talk about why? Because that's the big thing, right? You know, possibly I'm going to ask you, why does this happen? Okay, why does this happen? First one. The first one by definition, okay, by definition, boiling point going up is going to be based on colligative property number 2. Okay, that second property connects to the first. But first, we must know what it means to boil. So for example, what's the definition for boiling point? The point at which it bubbles, which is under what conditions? You're right. The second you start to see that, it's boiling. Correct. That's what separates boiling from evaporating. But when does that occur? Because evaporation happens all the time, right? Water's evaporating in this room. It's not boiling clearly, right? I'm happy it's not 212 degrees in here. Well, depending on the substance, right? Acetone boils really quickly. So, does anyone remember? You can look at your notes right now. Go ahead. Go ahead. Our water?
The point where a liquid changes from a liquid to a gas.
Correct. But under what conditions does that occur?
Under higher pressure.
It's possibly true, but something has to be the same for it to happen. Boiling point is when the atmospheric pressure is the same as the vapor pressure. And you can pause the video and start a new one. Because that should be within the 2 minutes. Yep.